So we've talked about how a transformation T can map vectors from one vector set to another vector set. And we said we might have something like this. So maybe we'll call this the subset A, and then this is the subset B. So we'll just name those here, A and B. So A is a set of vectors, B is a set of vectors, and we're saying that the transformation T maps vectors from the subset A to the subset B. And let's even go ahead and say that A is contained within R2 space and B is also contained within R2. So we'll say that this is R2 and this is also R2. And in that case, we'll say that T is mapping from R2 to R2. That means that we're going to be given vectors in the subset A that are two-dimensional vectors, and we're going to be mapping those to vectors in B, which are also going to be two-dimensional vectors. Well, now we want to zoom in on an even smaller part here of A and B. So let's say we have something like this part of A and this part of B, and we'll call this here the subset A1, and we'll call this the subset B1. And we're saying that A1 is just a part of A. So if A is a big collection of vectors, A1 will just be a subset of the vectors that are contained in A. And then in the same way, B1 will be a set of vectors that is contained within the larger set, B. What we're saying here is that the particular vectors in A1 are the vectors that map to the particular vector set B1. So the set A is full of a bunch of vectors, and a few of those are contained in A1. And then the set B is a big set of vectors, and a few of those that are in B are actually contained in B1. What we're saying here is that the set A1 is the particular set that maps to B1. So if we wanted to ask the question, okay, I know which vectors are in B1, which vectors in A map to those vectors in B1? What we're saying here is that it's not all the vectors in A, it's just this particular subset of A, A1. Those specifically are the vectors in A that map to these specific vectors in B under the transformation T. So it's the transformation T that's mapping from this subset A1 to the subset B1. And so when we have this particular relationship, we would call B1 the image of the set under the transformation. We would call A1 the preimage. So the transformation T takes the preimage A1 and maps it to B1, which is the image. Now we know from before, let's say that within A1, maybe I have some vector, we'll call this little vector here A1, and then I have another vector A2. Let's say that A1 specifically maps to a vector B1, and that A2 specifically maps to a vector B2, where B1 and B2 are part of this subset capital B1 in the image, and A1 and A2, those vectors, are part of the subset A1 here in the preimage. We already know that if we have some transformation matrix, let's say that transformation matrix is 4, -2, 0, and 3, that I just have to multiply that transformation matrix by any of the vectors here in the preimage. So let's say I multiply it by the vector A1, and I already know A1 maps to B1, which means the result here is going to give me the vector B1. Or similarly, if I take that transformation matrix and I multiply it by the vector A2, I know that the result I'm going to get is B2 because I already said that A2 is mapping to B2. We know how to go that direction. We know how to multiply the transformation matrix T by a vector in A to get the resulting vector in B. But we can also work backwards. So let's say that the vector B1 is equal to the 0 vector. And let's say that the vector B2 is equal to the vector, we'll just call it 4 and 1. If I know the vectors B that I'm getting out in the image, and I know the transformation T, I can work backwards to figure out which vectors in A mapped to those particular vectors in B. All I do is I take the transformation matrix and I augment it with the vector B. So in this case here, for the vector b0, 0, I'll just augment the transformation matrix with the 0 vector. And then I just want to put this in reduced row echelon form. So I'll divide through the first row by 4 to get 1, 0, and 0. And then the second row stays the same. And then I can add 2 of the first row to the second row. So I'll say 2 times 1 is 2, plus a negative 2 is 0. And then 2 times 0 is 0, plus 3 is 3. And then same thing over here, I get 0. The first row stays the same, 1, 0, 0. And then I can just divide through the second row by 3. And the result is 1, 0, 0, 0, 1, and 0. And then I can do the same thing with the second vector, 4, 1. So I'll just augment the transformation matrix, 4, 0, negative 2, 3, with the vector 4, 1, so 4, 1, and put this in reduced row echelon form. So again, I'll divide through by 4 to get 1, 0, 1, and then negative 2, 3, 1. And then I'll add 2 of the first row to the second row. So the first row will stay the same. 2 times 1 is 2. 2 plus a negative 2 is 0. 2 times 0 is 0. 0 plus 3 is 3. 2 times 1 is 2. 2 plus 1 is 3. And then I will divide through the second row by 3. So I'll get 1, 0, 1, 0, 1, 1. And now my matrix is in reduced row echelon form. My results then, my vectors in A, I can pull straight out of these reduced row echelon form matrices. So I get 1 here and 1 here because I have identity matrices on the left-hand side. Otherwise, we would have to solve these. But this here is telling me x is equal to 0 and y is equal to 0. And when I take those together, I can say the vector a1 is equal to 0, 0. And then same thing over here. What I'm getting here is x is equal to 1 and y is equal to 1. And when I put those together, I get the vector a2 is equal to the vector 1, 1. And so I can specifically say that under the transformation T, the vector a1, which is the 0 vector, is mapping to the vector b1, which was the 0 vector. And we said that A1 was part of this A1 preimage and B1 is part of this B1 image. And then I can say also that the vector A2, which was part of the preimage, and that is the vector 1, 1, is mapping to, under the transformation, the vector B2, and B2 we said was 4, 1. And so I was able to start with vectors in B and work backwards to find the vectors in A that map to them, unlike previously where we just took vectors in A and multiplied the transformation matrix by those vectors to get the vectors in B. So we're showing here that we can work backwards. And then the only other point we want to make, notice here in this example, we started with a vector in B in the image, which was the 0 vector, and we saw that the vector A, which was also the 0 vector, mapped to it. Well, any vector in your preimage that maps to a 0 vector in the image is part of what's called the kernel of the transformation T. And we write the kernel of the transformation like this, capital K-E-R for kernel, of the transformation T. And that's just all of the vectors that map to the 0 vector. So any vector that maps to the 0 vector in the image is part of the kernel. So in this case, because the 0 vector in A over here, this A1 vector, mapped to the 0 vector, we would say that the 0 vector is actually part of the kernel. But if we knew that we had vectors in A, let's say the vector 0, 0, the vector 1, 2, and the vector, let's say, 3, 4, and all these vectors are part of the preimage, and they all map to the 0 vector in the image, then all of these are part of the kernel of T. These three would make up the kernel of T because they all map to the 0 vector. So anything that maps to the 0 vector, which could be no vectors at all, or one vector or multiple vectors, but any vectors that map to the 0 vector are part of the kernel of the transformation.